All right, section 13.6 is about Stokes theorem. And when we're discussing Stokes theorem, we'll actually go back and we'll cover section 13.4, which was about Green's theorem. And the reason we went out of order here is because Stokes theorem is like a big formula, and then one very special case of it gives you Green's theorem. So kind of it's just a special version of the same formula you can go ahead and memorize. And I think it just makes more sense to do the more general one first, and then if you want to write that special formula down as we're going through this, you can. And we're going to cover this section a little different than we have past sections. Instead of giving you all of the steps, first, we're going to talk about what Stokes theorem is for and what it actually is, so you can write the formula down in your notes. And then we'll do examples so that you can kind of like get a feeling for how it works. And then we'll actually write down the steps once that makes a little bit more sense. So Stokes theorem is going to be a way to convert between surface integrals, which we recently covered, and line integrals for closed curves. And the particular way we convert is via this formula. So go ahead and write it down, and then we'll talk about what all of the different parts mean in a second. Okay, and so here's the Stokes theorem formula that you're always going to want to be able to refer back to. And it's going to help as we discuss this to kind of have, actually here, make more sense if I do that. I'm just creating a little picture that we can kind of talk about this idea with. So Stokes theorem is always going to be, you assume that you were looking at a closed curve. And so here's an example of a closed curve. It's something that has no holes in it. It starts and ends in the same place. And which way am I going to want that? I'm going to orient it this way. And you imagine that over that closed curve, somebody had asked you to compute the line integral of f. And what we're learning is that you can convert that request into the idea that you are over the corresponding surface. And when I say corresponding surface, I mean a surface that uses this closed curve as its boundary. So there's an example. The kind of like wobbly thing I drew to start. But another example would also be this one in the bottom. Either one, as long as it has an edge, and the edge is the green curve. So your surface should be open. So here's one example of an open surface. Just like imagine a hat with a hole in it. Oh, dang. Hold on. Or here's another surface. Same curve, just different way to fill in the gap. and the edge of this little disc is still that curve C. So I'll go ahead and leave the bendy one here because it's a little bit harder to draw separately. And then over here, I will say that disky shape is also okay. I think I accidentally changed colors, but I don't care. There we go. Okay. And then over that corresponding surface, we'll spend so much time talking about what that means, but you would compute the line integral of your curl, which we learned how to compute earlier in chapter 13. And I've denoted it as del cross F if you prefer that way to remember curl. But if you just committed the curl formula to memory, that's also fine too. The only tricky thing here is that your surface integral has to use a normal vector with appropriate orientation. And so for the problem I drew, appropriate orientation would be like this, oriented outwards. But normal vectors just have to be perpendicular to the surface, so there's no reason why a generic normal vector couldn't be pointing into the surface. And that orientation is going to have to come from what's called the right-hand rule. So if you curl your fingers along C using your right hand, your thumb should point in the same direction as N. I'm going to try to do this. So here's some fingers. There are 4 of them that aren't thumbs. Great job. And then there's a thumb. Okay. So here's a right hand. And what I've done is I've had the right hand's fingers curling in the same direction as that curve C I drew before. See, that one went that way. Imagine the palm is kind of like facing into the curve, and then you're wrapping your fingers around so that you could follow the curve. So it's doing that thing right there. And then the thumb is pointing upwards. And so that's why I decided that these normal vectors had to be pointing up and out. If the normal vectors were pointing down, then they would not be pointing the same direction as the thumb. That's going to be our right-hand rule. If you do it a few times, you'll get the hang of it. If it's hard to tell from these pictures, just kind of ask me during class and we can do like the physical demonstration of the right-hand rule, not using this bad picture of a hand. So the setup for these problems is going to be really complicated because what we're going to have is given usually a closed curve and a line integral request for some vector function f. We have to identify the surface. So there's going to be choices and you have to pick the easiest one. And then you're going to have to pick the normal vector that goes the right way, or else you'll get like negative the correct answer. And then you'll have to compute the curl, which is probably the easiest part of the problem, except that computing curls is never really fun. And then you have to set up the bounds for your surface integral and evaluate it. Okay, this is very long. So we'll go ahead and stop here, and we'll talk more about motivation when we discuss the steps later.